Hi guys, welcome to Goodwill Gate to IIT. I'm Prateek. So this lecture is basically a special lecture for computing the deflection of beams under different loading conditions and different boundary conditions. So the great you can say background about this lecture will be discussed in module 2, which is the complete aircraft structures. Now this lecture typically focuses on how to compute the deflection of beams, particularly focusing towards the gate problems. So without wasting any time, let's continue what we'll be doing today. So I'll be discussing a very special method, which is virtual work method, and we'll be using unit load approach in that to compute deflection of beams. Now deflection of beams we have seen in during our BTech, and how to compute deflection of beams by using Maclaurin's method, in which you need boundary conditions to solve the value of deflection or the slope or movement at any point. But in GATE, if we apply that procedure, it will take for around about a very simple beam, it will take some like 10 minutes. Or if you are very good in your calculations, let's say 5 minutes. But you cannot afford to spend such amount of time in your GATE exam for one numerical. So we need a shortcut, and that too without any calculation mistake. So let's start on this. So I'm not going into the theory of this. So what I'll do is I'll give you a formula. Use that formula and solve any problem for calculating deflections or slope or movement about any arbitrary point on a beam, irrespective of its boundary conditions. Alright. So this method is basically virtual work method. Its explanation you will find in the module 2 lectures. But let's see how to compute deflections directly. So when I say, just keep few points in mind. So what we'll be computing is we are interested in calculating the deflection at any arbitrary point. Alright, so my motive is to, let's denote this by delta. So what I'm going to do in virtual work method is I'm going to apply a unit load. Now this is a virtual load, it is not actually present. So we'll see how to solve the numericals. So 1, which is load, into deflection. Load into deflection is nothing but the work. Alright, so for this reason we are naming this as virtual work method. Now what the formula you just need to keep in mind is integration over the entire length of the beam, which we'll be dividing depending upon the problem. Alright, capital M into small m divided by EI. Now I'll explain each and every term in this, and you integrate this over the whole length. Now in this E we know is Young's modulus. I is the moment of inertia, area moment of inertia of the cross section. Alright, so capital M, just keep few things in mind. Capital M is the moment of the original beam. Alright, and small m is the moment when we apply our unit load, which is virtual load actually. It is not actually present. Alright, so to get familiar with this, now there is a particular derivation for this, explanation of each and every term, which you will find in module 2 detailed lectures. Now in this particular lecture we will be focusing directly on how to solve the problems. So let's take a simple example. It looks simple, but your motive is to remove the calculation mistake and save time and quickly arrive at the solution. So we have a cantilever beam, alright, and you have a point load exactly at the free end. So your motive is to calculate deflection at this point. Let's say this point is A. So your motive is to do this, calculate deflection at point A. So today I am discussing only deflection. You can calculate slope here also. Alright, so we know this expression. This is basically, if you say the length of the beam is L, so deflection should come out to be PL cubed by 3EI. If E is the Young's modulus and I is the area moment of inertia of the cross section, it can be anything. It can be a rectangular or a circular section, or I section, or Z section, or C section. It can be anything. So your motive is to calculate deflection of this cantilever beam. And the advantage of virtual work is you need not to compute, you need not to worry about the boundary conditions. This is one big advantage of virtual work method, because you're calculating work, like something like energy. So you're computing that. On the other hand, in Maclaurin's method, you first need to compute the you first need to calculate the reactions, and you should know the boundary conditions properly. Then only you can apply, and it will take longer time. Alright, so what we'll do, this is the original beam. So this original beam will give me capital M. So what I'll do is I'll write capital M for this. Now many people have doubt in this. What is the sign convention need to follow, and which one is positive, which one is negative? So for your reference, if this is the beam, these are the bending moments I'm going to take as positive. This is positive bending moment. Let's keep that thing in mind. That's it. So always make a habit of doing this. What I'll follow is, it's not hard and fast rule. You can move by the other methods also. I'll always move from the right hand side. So let's say X is measured from that side. So X is equals to 0 here, X is equals to L by 2 here, and X is equals to L here. So X is varying in this direction. I hope it is clear. And with this sign convention, what we'll see is all downward deflections comes out to be positive. So any deflection if comes out to be negative, that means the beam is getting deflected in the upward direction. From this, the beam is getting upward. From this, if beam is getting downward, this is positive, and upward it means it is negative. So make a habit of doing this. Always start your X from this. So 0, L by 2 and L. I hope it is clear. Second important point. Never calculate reactions if you have a cantilever beam. It is not required. Alright. So I always move from free end. If a cantilever beam is given something like this, if a cantilever beam is given to you like this, put your X here. So X equals to 0, X equals to L by 2, and X is equals to L. So in this way, you are actually not to calculate the reactions. You can omit that thing. And it's easier to write your capital M equation. Right? So when you want to write that, assume any arbitrary section which is at a distance X from the free end. That means X equals to 0, and here X is, this length is X. So what is movement about this point? Tell me. So this is the point load. So P into this distance. This is nothing but X. Alright. And when you're moving from right hand side, you need to see, this is my positive bending moment, right? So this moment, which is load is acting downwards. So load is acting downwards. So it will be this movement, right? This movement, this movement. So it is exactly opposite to my sign convention. So I apply a negative sign. Now, as you move from this point to this point to this point and this point, and then you move forward, this movement will change with respect to X. So it's a linear function of X. I hope it is clear. So X can take values from 0 to L. I hope it is clear. So we need to practice more numericals to make command on this, but I'm trying to go with the very basic thing. Alright. So what you'll do in the next step is, this capital M is clear. So what I'll do is, I'll draw the entire beam again, and you stop at this point. Don't apply any load. Whatever external loads are given to you, don't apply them. So maybe UDL, maybe a point load or a point movement, whatever is given to you, remove all the external loads. And at the point where you are interested in calculating the deflection. So in this numerical, my motive is to calculate deflection at free end. Alright, so I want to compute this. So what you'll do is apply a unit load, point load. Apply a point load at that particular point where you are interested to calculate the deflection. So I want to calculate deflection at point A. So I have applied deflection at point A. Unit load at point A. So don't think that I've applied unit load here because there is load present here. No. If I want to calculate deflection at center point for this beam, I will apply unit load at this point. I will not apply load at this point. So wherever you want to calculate your deflection, at that particular point, apply a unit load and remove all the external loads. Alright, again follow the same procedure. This is X. I am assuming some section. The length is L. Now when you calculate movement for this becomes small m. So this is 1 into X. And this is again in the opposite direction of our sign convention. So I apply a negative sign. And this goes for all the beam, for the entire beam. I hope this is clear. Alright, so keep basic formula in mind. 1 into deflection, integration 0 to L, capital M, small m, EI, dx. So capital M equation you have, small m equation you have, E and I values are not going to change for a particular beam. and integrate this over the entire length. Alright, so capital M value is minus px, small m value is minus x. Alright, so let's substitute those values. So what I have is deflection at which point? At point A, because I have applied a unit load at point A. For that reason I am getting deflection here. Is it fine? So integration. Now this moment equation is valid for the entire length of the beam. This moment equation is valid for the entire length of the beam. So I'll say 0 to L. Capital M is minus px. Small m is minus x divided by EI dx. I hope this is clear. So what we'll do, we'll just integrate this. So just solve this numerical. So this becomes p x square divided by EI dx. Alright, so if I'll integrate this, this becomes p x cube by 3 EI between the limit 0 to L. If I'll substitute the upper limit and the lower limit, the deflection at the free end of a cantilever beam under point load comes out to be PL cube by 3 EI. Now guys, because I have given the explanation, so it has took some 5 or 10 minutes because we are doing this for the first time. Now you can imagine if you apply this method, write capital M, write small m, substitute in the expression and integrate it. This will hardly going to take 1 minute or 2 minutes, which is good for your GATE exam. So if I'll go solve the same numerical, which is this is known as the easiest beam, right? So if I'll go for this using Maclaurin's method, it will easily take 5 minutes. Along with the calculation error, there are possibilities of calculation error and there are possibilities of spending more time, which is actually not required. I hope this is somewhat clear. So let me do one more problem. Let me solve a problem which is somewhat, you can say not complicated, but let's say somewhat different boundary conditions. So if we have let's say a simply supported beam, all right, we have a simply supported beam and you are applying a UDL over it, which is small w unit per unit length, and the entire length of the beam is L. Is it fine? So what we'll do in this, exactly same procedure, but guys, keep one thing in mind. When you're solving simply supported beam, you have to calculate reactions first. In cantilever beam, we are omitting this because we are moving from free end. But in simply supported beam, we have to calculate reactions first, then we should proceed forward for calculating the deflection of the beam. You cannot calculate deflection of the beam unless and until you have reactions. I'm saying simply supported beam. Alright, so I'm doing this directly. We'll discuss this how to calculate reactions separately in some basics class. So I'll tell you simple basic. What is the entire load acting on this beam? So small w is per unit length. That means it is uniformly distributed and the total length of the beam is capital L. So the total load acting on this beam is small w into capital L. Small w into capital L. So to visualize this, don't do this. Just think in your mind. This small w into capital L is the load which will be acting exactly at the center point. This is your visualization. So you are converting your UDL into a point load exactly acting at the center of the beam. I'm not going to draw this, but you should visualize this. Is it fine? Okay. So W into L is the entire load. So half of will be taken by the roller support and half of it will be taken by the hinge support. There will be no horizontal reaction because there is no horizontal force, and hinge support as well as the roller support don't have any movement. They don't resist any movement, so there are no reactions present. So if I'll draw a simplified beam for this, I'll do this. Let's say this point is A, this point is B. So this is point A, this is point B, and you are having a UDL of small w per unit length and length is capital L. So what will be reaction at B now? Total load is small w. So half of it is supported by this support and half of it will be supported by this. I hope it is clear. So now we have the reactions. Let's calculate the deflection. Let's say calculate deflection at center point. They can ask at any point, like say L by 4 from here, L by 4 from here. We are calculating just to understand how it works exactly at the center point, because we have a result for this. So tell me capital M. So what I'll do is I'll start again from this direction, X. At this direction you assume any section. So how many movements will come? First, this force, which is a point load, whose magnitude is WL by 2, will going to produce a movement in this direction. Alright, so this direction movement. So it will be W into L by 2. Now this is the load into X. Now I am applying positive sign here because it is following my sign convention. On the right hand side it is doing this. Alright. Now at this section there is some UDL present here, right? Don't worry about anything which is happening on the left hand side. Only see what is happening on the right hand side of the section you have considered. Don't consider any force on the left hand side. So W into L by 2 into X is the movement produced by the unit load, the reaction. And now this load will produce a movement in the downward direction. So I'll apply a negative sign. But this is UDL, right? What is the magnitude of this UDL? Small w. It is acting over this length only. Alright? So it is acting only on this section. What is this length? X. Is it fine? Now, I told you initially how to take movement for UDLs. This is acting along length X. So in your mind you visualize that W into X is the load acting on this section of the beam, and you assume that it is acting here now. This is purely your assumption, guys. Don't draw this. So movement is always force into perpendicular distance, right? So force is small w into X. So small w into X will be, let's say, acting at exactly at the center point. So what is this distance now? This total is X, so this will be X by 2. So I'm just going to multiply this by X by 2. So this is the way of how we take moment of UDL sections. Alright. So capital small w L by 2 into X minus W X square by 2. This is a capital M. Alright. Now what I'll do is, you want to calculate deflection at exactly the center point, right? So draw the beam again. Remove all the load. So UDL was present, I am not drawing it. Because of UDL, what reactions are coming? I am not writing it. Where you want to calculate your deflection? Exactly at the center point. So let's say this. So L by 2 here and L by 2 here. Alright. So apply a unit load at this section. Let's say 1. So when you apply unit load here, 1, some reaction will come here as 1 by 2 and some reaction will come here as 1 by 2. Alright. This will clear all your doubts. So let's start writing small m. So what you will do writing small m? Start your X from here. Assume any one arbitrary plane here about which you are calculating a moment. So what is the force? 1 by 2 into this distance X. It is positive, right? 1 by 2 into X. There is no other force on the right hand side now. So stop here. Till what section you can move? So if I'll move in this zone, still I can say 1 by 2 into X. Now actually you are moving your X arm. So 1 by 2 into X, 1 by 2 into X, 1 by 2 into X. Stop here, because now at this point some other load is also coming. So till what range X can vary? So X can start from 0 and can go till L by 2, and this equation is valid then. So I'm going to write that this is X is going to vary from 0 to L by 2. Now what you'll do? Now from this point onwards, if you go to this side and assume something. Now again keep this in mind, you are moving from here only. X is 0 here. X is L by 2 here. Alright. So you are moving after L by 2. So what is the movement produced? Now what are the forces acting on the right hand side? Completely. So you need to have two equations now. So 1 by 2 into X. Now X is this distance this time. So X is this distance this time. So I'll say 1 by 2 into X. Again it is in the positive direction. Alright. Then there is no force. Then the force comes here. So this 1 will produce movement about this point. because it is in the downward direction, so I'll say minus 1. I need this distance now, guys, this distance. So what is this distance? 1. This total distance is x. This is L by 2. So this remaining distance will be x minus L by 2. So 1 into x minus L by 2. Now this equation is valid only in which zone? This equation is valid only and only when your x is between this. Now this is somewhat complicated practice you need to do so that you can understand these equations. So this equation m is equals to 1 by 2 into x is valid only for this zone. And this equation, which is 1 by 2 into x minus L by 2, is valid only in the complete zone. So just a quick note for your gate. Whenever a point load comes like this, whenever you are moving along a beam and a point load comes, you have to write a separate equation for that. You cannot proceed with the same equation. This is quick hint. This is an advantage with UDL. UDL is we will never going to stop. So only one equation is enough. Now you can see in the previous problem, see, we were writing only one equation, right? Because there was no point load in between. I hope this makes some point clear. Alright, so what is the next step? Go to your main equation. What is your main equation? 1 into deflection is equals to, now your formula is integration over the entire length of the beam. Now the length of the beam is actually divided into two portions, 0 to L by 2 and L by 2 to L. On the other hand, capital M is described for the complete zone. See, capital M is same for the entire beam, right? 0 to L. So, excuse me. So 0 to L by 2, this is capital M and this is small m. From L by 2 to L, again this is capital M, but your small m is this. So your integration is divided into two parts now, 0 to L by 2 and L by 2 to L. I hope this is clear. So integration 0 to L by 2. I'm going to write capital M now. WLX by 2 minus WX square by 2. Sorry, these are same W's. This is capital M into small m, which is x by 2. So I'm taking EI outside into dx. This is one portion. Plus 1 by EI. Now it is L. Write your capital M again. Capital M is same for the entire length, right? So whether it is 0 to L by 2 or L by 2 to L, capital M remains same. But what is a small x now in L by 2 to L? This is x by 2 minus, let's say, x minus L by 2 dx. You solve these two integrations, you will get your deflection of the beam as 5 WL to the power 4 divided by 384 EI. Now this looks complicated, time consuming, but frankly speaking, if I start solving the gate problems right after this will be straightforward, saving your time. And the main advantage of this method is you can compute deflection and slope at any point of the beam where you want to calculate. Alright, so I'll be practicing, we'll be practicing more numericals on this. I'll give you more numericals for your practice, so just verify the solutions. And we'll have a second lecture for this itself, in which I'll tell you how to compute the moments. And we'll try to solve few types of cantilever beams and few types of simply supported beams or overhang beams using this method. So what you can do is start practicing deflection of the beams using this method and verify your solution, which you are already solved in other books by other method. So what you can observe is you can actually reduce your time to half once you are using this method. I hope this lecture helps. So I'll be posting the next lecture as soon as possible. We'll be posting it really soon. So let's stop here, and if you have any queries and if you want me to solve any particular problem related to deflection of beams or any special topic you want to understand, you are having doubt in, please write in the comment section. We'll be trying to post a lecture on that, and you can visit us at www.goodwillgate2it.com. You can message us, call us at the displayed number, and you can write to us at info@goodwillgate2it.com. And please like, subscribe and share, and Good luck. Prepare well. Thank you guys.